Hello, in this video, we'll be expanding on semiconductors. We're talking specifically about transistors. Now, transistors are an important aspect without which modern computing and many electronics would not be possible. I'll be talking about their history, the different types of transistors, and how each works. So what is a transistor? Well, the most general definition is a semiconductor component used to switch or amplify current or voltage and possessing three terminals. The first proposal for a transistor came in 1926 by Julius Edgar Lilienfeld. Although the first constructed transistor was invented in 1947 by Bardeen, Bratton, and Shockley at Bell Labs, and it just consisted of a block of germanium and some gold metal contacts, and this was called a point contact transistor. It was eventually reconstructed by hobbyists as part of the wave of hobby electronics that came out post World War II. Bipolar junction transistors came out just a little bit later and became the first practical transistor that was mass produced, which allowed it to slowly replace vacuum tubes and many electronics. And by 1954 was a miniaturized radio that could fit in your pocket, which consisted, I think, of only about a dozen transistors. MOSFETs came out in 1959 and they slowly replaced bipolar junction transistors and a lot of electronics, but there's a lot of other types. There's JFETs, which came out a little before MOSFETs, IGBTs that came out in the 80s, MESFETs, HEMTs, which I believe came out in the 70s, IDFETs, FinFETs, which have been replacing MOSFETs and chips since I want to say the 2010s. TFETs, CNT and GAFETs, which are just been introduced to the market and are going to slowly replace FinFETs. All right, I'm going to go over the history of transistors here. I'm not going to go into all the history of semiconductors as that's in another video. But the 19th century basically saw the properties of semiconductors discovered, so that by the early 20th century, we saw diodes, vacuum tubes, and the birth of radio. Between the 1900s and 1930s, there was an explosion of new theories, understanding how everything from atoms to electricity worked. And then, as I said, 1925, 26, the first device similar to a field effect transistor was first proposed. In 1947, we saw the first point contact transistor, which finally made the idea of transistors a reality. In just a few short years, in 51, 52, we saw the first transistor hearing aid. In 54, we saw the first transistor radio, or at least the first mass produced one. And at that point, now radio was something you could fit in your pocket. In 58, we saw the first working IC, along with 59, and also in 59, first invention of the MOSFET. A few years prior to that, I couldn't find an exact year, is when the first was when the JFET was conceived. But it wasn't until the early 1960s that the first practical JFETs came about. In the early 80s, we saw the first practical IGBTs. And then somewhere in the span of over 20 years, and many different researchers and inventors, eventually led to the FinFET. And by 2012, the FinFET was deployed en masse, which basically surpassed MOSFETs in high density chips. And now in 2022, the first deployment of GAFETs, which are meant to eventually replace FinFETs entirely. All right, so there's a lot of different types of transistors, sort of putting them in two categories of bipolar and unipolar. Um, Although there's some argument on this. The first one was the point contact transistor, which, as far as I know, I don't think you can readily get anymore. There may be niche markets possibly for old parts. I really don't know. Bipolar junction transistors, which are going to be one of the most common we talk about, and then the IGBTs, insulated gate bipolar. We may eventually get into that, although it's ubiquitous. It's all around us. And then unipole ones, which split into the field effect or FET. There are no FET transistors. They're all going to be subtypes. We've got the MOSFET, the metal oxide semiconductor FET. You got double gate and power versions of those. That's the second one we'll be talking about the most. JFETs, junction FETs. We'll probably be doing some talking of those as well. FinFETs you're already experienced with and you don't know it. Basically, every CPU, GPU, and whatever is probably full of them. Basically, they call them FinFETs because part of it is now 3D and sticks out like a little fin. And then we've got GAFETs, which are going to be replacing FinFETs. I think they're already starting to, um, which is a gate all around. We've got MOSFETs, which are metal semiconductor. I don't have a whole lot of experience with those. HFET, which is just heterostructure. We may be talking about HEMTs, which are high electron mobility transistors. We've got TFETs, OFETs, CNT FETs. That's carbon nanotubes. That's a new technology. Graphite FETs and ion sensitive FETs. Some of these we won't even mention, although future videos on some of them we're going to go into more detail. All right, the first transistor we're going to really talk about is bipolar junction transistors. And effectively, the work on the first transistor, which is point contact, led to bipolar junction transistors. And by 1954, they were purchasable, actually, probably a little before that. Um, Basically, revolutionized electronics and was the beginning of the end for vacuum tubes. You'll either see them at NPN or PNP. Functionally, there are two semiconductor junctions joined together. If you want to know more about the science, watch my video on semiconductors. You've got collector on one end, emitter on the other, base in the middle. The base controls the flow from collector to emitter. Smaller current controls flow of larger current. Basically operated in three states: cutoff, the base voltage is too low, um, the base emitter junction just doesn't conduct, and there's almost no collector current. And then you've got active, where it's amplifying. You turn it up, it amplifies more. Basically, the base is just slightly above the current, slightly above the emitter, sorry. And you're getting a small current controlling a larger current. And then saturation is basically it's just flat out on. So the collector's too low, no more gain. Collector and emitter basically shorted is like an open circuit. If you're switching, you're looking to go between cutoff and saturation. If you're amplifying, you're going between cutoff and active. Oversaturation is going to be too much base current, and turning it off again can be relatively slow because you get a buildup of charge in the base and the collector. I can't think of any applications where oversaturation is actually a good thing. Here's a quick example of a bipolar junction transistor in the TO92 package, which is probably going to be the most common ways you find them. Again, you've got emitter on one end, collector on the other. It's not guaranteed that they'll be laid out this way, so always consult the data sheet, and the base obviously is always in the middle. Information is probably on the flat side so that you can actually look it up. Some of the specs that are important, if it's NPN, PNP, that's the first biggie. The location of where the collector and emitter, it can be one order or the other. There's not a guaranteed standard. What kind of package type? We just looked at TO92, but there aren't the only ones. Usual stuff about voltage, current, and temperature maximums. You've got collector emitter voltage, you got collector current, you got power distribution, which is usually a matter of maximum heat in watts. Probably not going to be much of an issue at low level hobby electronics. Max temperature for the junction, DC current gain, how much basically the collector current for a given base current, the base emitter voltage, basically how much voltage you need to turn the thing on, as I understand it. Saturation voltage, basically the voltage across collector emitter when it's saturated, and then frequency response speed, which low level hobby electronics until you kind of get up there in speed for switching, probably not much of an issue. Now, I mentioned TO92 being the most common package you find. However, there's plenty of others. You may find the older metal cans package. It really depends. I mean, those smaller packages, that's going to be for small signal. Moving into like medium power, There's a couple ones you'll encounter, and they usually have a heat sink of some description on them. Since they're meant for more power, it will give off more heat because remember, electricity dissipates as heat. So if you find a TO220 package, that could be a MOSFET or it could be a medium power BJT, so always check the specs for what it is. There's some surface mount ones. If you look on circuit boards, the most common I've found is the SOT 23. You'll see a little flat package with terminal on one side and two terminals on the other. And then there's some other ones. Um, Here's just a picture of some of the other forms you might run into. The TO03, you'll see that a lot in electronics. You may eventually use it in hobby electronics, but it's not easily breadboard friendly as far as I know. I mentioned the TO220 and the similar T22L5. Again, people sometimes mistake these for MOSFETs, and you've got some surface mounted options as well. Then here are some of the common BJT models you'll run into. I want to say the 2N2222, and it's PNA variant. You're going to find these in hobby kits. If it comes with a transistor, will probably come with one of these. And then it has a complement, which is usually the PN207, 2907, I'm sorry, which is PNP. A lot of times, two types of transistors, an NPN and a PNP, will be considered a complement of each other. But there's usually a bit of range to that, depending on what you're working with. You've got some others, the 2N3904, kind of similar to the one I just mentioned, and it's less forgiving as far as I've read. All the bold underline ones are ones I definitely have in my collection. Um, and then stuff with the BC in front, that's British, European. You're more likely to encounter a BC 327 as opposed to the 2N2222. Um, but yeah, that really depends where you get it from. So yeah, these are just some of the ones you probably encounter. Now, I mentioned for what's known as a Darlington pair or Darlington transistor. When it's called a Darlington transistor, that confuses people. They think it's some kind of new other transistor when it's not. It's just a connected pair of BJTs. The emitter of one simply goes into the base of the second. Well, what does this provide? Provides even more amplification of a signal as the base of the first amplifies an already amplified signal. Has very high sensitivity to changes at the base of the first one. Some downsides, there's a higher voltage drop. You could be upwards of needing twice as much. Slower switching, but that's more of an issue with the transistor itself. And you've got even more heat because you're dealing with two instead of one. It's good for low frequency switching, motor control relay drivers, some older power amplification applications as well. You'll often find it in IC packages that provide multiple pairs, which those can be great for hobby electronics, as in addition, they probably provide some additional protection with inductive or high current loads. Generally speaking, modern designs have replaced them with MOSFETs, though. All right, let's start taking a look at every circuit here. I've already, I think, shown these examples in my semiconductor, so I'll try to be brief. All right, so if we move it up, gonna take a little bit. We're into the millivolt range, still nothing. Started to get something there at about 10 millivolts. Actually, that might just be noise. Oh, start getting noise out of the blue there. So we're starting to get, so let's see, let's bring this back up. All right, now we're getting some actual effect. It's still just in the nano amps. Let's keep moving it up. And now it's going even more quickly. We're into the micros. Now we're into the milliamps. So we're into the active phase here. Oh, and of course our light is now lighting up around 0.7. So let's see how far we can take it before it starts to plateau, go saturation. About there. That sounds about right. So at about 0.78 or so, we're going into saturation. And it's no longer going to respond, it's just flat out on. So, if we wanted to just use this as a switch, we'd want to take it to 0.758 volts or so. Um, yeah, this seems to be a good range right here. So let's see what else we have. Now in this case, resistors have been used, so it just is a switch. We're getting the exact amount of power that we want. And in one case, it's NPN, and the other case, it's PNP for basically the same effect. Turning off the power to the base, turning off the power to the base. All right, in this case, we're using a pair of transistors that are each feeding into each other. Actually, we got to get this started. So there we go, blinking back and forth because one is fed back into the other through a matter of capacitors and resistors. And these outer resistors um, are just basically controlling the LEDs. Then here is the same idea, but I believe this is P and P. Yeah, P and P. Slower, I mean, I'm not using the exact same values, but the idea is still the same. Here's a logic gate made using 2 transistors and 3 resistors. Actually, I guess technically with a logic source, that's not necessary. It is a, yeah, NAND gate. So it'll be true, the light will light up for anything but 1 and 1. 20 milliamps, 2 volts, so very precise. And I believe that's why I selected the transistors I did. All right, this is a NOR gate made with them. So as long as it's not OR, it'll light up. So there, doesn't. And then now here's a Darlington setup with NPN transistors. Just using it as a switch here. You've got very little, in this case of using this, um, you've got microamps, literally just 1.51, which is feeding into this, oops, first transistor where it's outputting, see, this is all on 5 volts here, um, outputting to the second one, and that's becoming 15.2 milliamps. And actually I have a resistor here so that the light's not getting blown out, but it's coming out to 15.4 milliamps at 1.97 volts. And again, the entire trigger for this is just 1.51 microamps, so basically next to nothing. That's the kind of amplification you can get out of this. All right, let's see some stuff with BJTs in Falstead. So transistors. So basic thing is using hundreds of microamps to drive order of magnitude of milliamps, actually far more than we would need. And this is only 2 volts here. Still have to drive down the milliamps, I think, but another transistor, same idea. Let's look at a switch. See, our base is 433 microamps, but it's conducting 16.309 milliamps. Um, voltage is from emitter to collector a little low to put it in a light, but you get the idea. Emitter follower. Okay, here's a vibrator similar to what I did on every circuit. Same idea. I just don't have pretty blinking lights, but you can tell it's basically the same, more or less the same waveform down here. Let's see, here's a bistable one. Now, this is basically turning it into an SR latch, which we'll get into in a later video. But we're doing it with transistors here, and this could be actually the inside of an SR latch right here. So this is a way how smaller components can fit into something like an IC. Unstable one. It stays on for a little while after we've done it. Now here's just a basic amplifier setup. It's amplifying the signal from half a volt to over 5 volts. That's just scaling with the waveform scopes here, so ignore that. Look at the actual numbers. Let's see what else we got. Uni gain phase splitter. So we got 2 outs. Again, this is centered around a BJT. It should give you an idea. Then moving on, we've got field effect transistors or FETs, and this is any transistor controlled by an electric field at the gate. Keep in mind, this is more of a concept than a specific type of transistor. You're not going to find just FET transistors, are going to be something else. So instead of that PN junction, we've got a gate that creates an electric field, and that electric field is actually what controls the flow instead of the gate directly. That's why we use the term field effect. We've got a gate instead of a base, a source instead of a collector, and a drain instead of an emitter, and that basically reflects the difference. It's controlled by voltage instead of current. It's unipolar, not bipolar, so it's P channel or N channel, with most of the substrate being the opposite. So if you've got a P channel, the substrate that takes up most of it is going to be N layer with a flow between two small P layer or N layer. Again, if it's an N channel, that flow between those two little pieces is going to be an N layer. It's much more higher efficient. It can handle switching much faster, orders of magnitude, very low input current, and easy to make at a very microscopic level, which is why it replaced BJTs. They also can come in enhancement mode, which is normally off, so you actually have to apply voltage to turn it on. You're going to find those a lot more, but there's also depletion modes. They're less common, but they're normally on, so applying voltage turns them off. So keep in mind of that difference. Here's just a little illustration from DigiKey on how it actually looks. You've got your doped regions, and then you've got your body substrate. This kind of shows the action here. The key thing is the electric field that's being created, and that's actually what creates the induced in channel there. Um, All right, now we come to JFETs, which were the first practical FET whose development began just after the invention of the transistor, although the mass-produced JFETs didn't really start showing up until the 1960s. Some people regard them as basically the simplest FET that's on the market. They're voltage controlled but conduct current. They're always depletion mode, normally on, just because of the nature of a JFET. It uses a reverse bias PN junction as the physical structure of the gate, but the actual control mechanism is still the electric field. And you've got N channel and P channel JFETs. N channel, you remember electrons, it goes from drain to source, and the gate starts at 0 and it goes to negative voltage, which again is partially why um, it can be difficult to use in hobby electronics. P channel is the opposite, but it's extremely rare for a JFET. Holes source to drain, and the gate is from 0 to positive voltage. Keep in mind, JFETs, they're designed, they really aren't the best for logic level signals since it's an analog depletion device and not a clean digital switch. But it can be used as an analog switch. There's one model I found that's pretty readily available that you might be able to use for things. It's a good general purpose model, and that's the 2N5457. But keep in mind, it's usually working with like 6 volts, 10 volts, whatever, which is beyond 3.3 or 5-volt logic levels, but it is pretty good for audio preamps. Here's a little illustration of a JFET. Now, keep in mind, it actually doesn't have two gates. The gates just kind of wrap around together, so you really just have one gate. Oh, well, actually, no, you see the two gates being joined there, and you've got your drain and you've got your source. Um, All right, now we're looking at an N-channel JFET in Halstead. Got a 5-volt source here going to an LED. It's currently at 0 volts. It's basically negligible power here. In real life, with a model, it might not work this way because this is a very generalized model. Let's adjust the gate voltage up. So yeah, the current's going. Mind you, this is supposed to be voltage controlled current conducting. So at this point, we get we definitely see the LED at 2.2 volts. We'll keep doing, but notice at 1.7, it's pretty holding pretty steady on the volts. And eventually at 5 volts, we've got 12.2 milliamps and 1.8 volts. Let's continue to take that down. And actually, now at 0 volts, we still got 1.5 volts going through, and but our current is negligible. And let's take it in the other direction, and it keeps going down. So eventually, we get down to a point of I don't know. Let's just say negative 3.9. Real life JFETs are not good as switches. They're more like clamps. All right, we're in QSpice now, and we're going to be plotting current versus voltage here. This is the kind of thing that you would find in the data sheets for a JFET. So we're taking our source between 0 and 10 volts, and we're doing steps with the gate voltage starting at 0 and working backwards because this is an in-channel um, depletion mode JFET. I don't really need to mention the depletion mode part. So let's run it and see what we get. All right, here's our plot. So basically, each of these is a different gate voltage. And here's our gate voltage down here. And then the plotted lines would be, I believe, the source. So you'll notice at 0, yeah, there's pretty much no current. But as we get to, I would say, this is, I should say the plot, sorry, the plot is the current of the drain of the JFET. But yeah, once we kind of get up there, it starts to break apart. And I would say about yeah, about 1 volt on the gate. That's where we see our first line, and that stabilizes. And mind you, there's a bunch of lines under here that are just flat out 0. So these are probably the highest 3. So they are probably -2, -2.5, and -3 respectively. Yeah, 2, 2, 5, 3. Okay, I think that's the, yeah, yeah. All right. So this first one is if we're kind of ampage we're getting with the first step um, as we go through here, and then 0.5. 3. Um, Assuming I'm reading these plots correctly, I'm still pretty new to this. But yeah, it only gets up to like third of a milliamp, and it's not until at -3 here that we can get pretty high up here with like 2.0, 2 points. Yeah, we get a pretty high up there, like 2.7 whatever here. Um, but yeah, there's a plot for the JFET. Hopefully, we'll get into some more advanced stuff with later videos. And then we have IGBTs, and they're considered sort of a sweet spot between BJTs and MOSFETs in that they can handle higher voltages than MOSFETs. They started making the scene in the early 1980s. Easy voltage control of a MOSFET, while the high current, low loss of a BJT. It has an insulated gate. Um, it says the insulated gate of a MOSFET basically, but the conducting is actually handled like a BJT, but it's not quite a BJT anymore at that point. Um, Voltage controls current flows. Really good for high power applications, trains, automobiles, power grids, UPS systems, etc., because it can take the voltage. You're probably less likely to find these in hobby electronics, like you won't probably see them in a kit, but you can still buy them pretty cheaply, like the price of MOSFETs. But you're definitely dealing with them if you deal with any of the applications out there. Um, but keep in mind power requirements, just like with MOSFETs. So make sure you find something that works at hobby electronic levels. If you've got something that's not going to kick in until 10 volts, less likely something you could use in hobby electronics. And here's an illustration of how they work. These I'm a little less familiar with. I actually haven't worked with them directly yet. But you've got your collector emitter, but you have a gate. So you've got this interesting mixture here. Um, then we've got high electron mobility transistors, which are a subset of heterostructure uh, field effect transistors. Basically, there's a junction between two different semiconductor materials, which is known as a heterojunction, with a layer where the electrons can move really fast. So this is good for extremely fast switching and very high frequency operations. You got RF amplifiers, fast chargers, microwave systems, high frequency power supplies. I think the more modern versions use like gallium nitride. You probably won't encounter these as directly, but if you're using USB-C power delivery, then you're already using these. Here's a little illustration. You got your source, gate, and drain, but you have all these different layers. All right, now we're moving on to MOSFETs. That simply means metal oxide semiconductor FET. And that really just describes the construction of the gate, which is made of metal, aluminum, or I guess nowadays it's polysilicon. An insulator is made of oxide, usually silicon oxide, and then the body channel being the semiconductor. They were invented in 1959 by Mohammed Atella and Dawang Kwang, and they quickly just dominated electronics. And they made them smaller, less heat, far more efficient. I'm not even sure personal computers, much less smartphones, would even be possible today without them. Eventually, FinFETs got rolled out in the 2010s, and they've replaced MOSFETs in processing units, CPUs, GPUs, NPUs. There are so many PUs. There's a list. And then GAFETs are just starting to roll out, and eventually they're probably going to replace FinFETs. The first ICs using MOSFETs came out around mid 60s, and initially they were just PMOS, which is P channel MOSFETs. MOSFETs also may not give you the desired behavior if you're trying to use them as just a simple switch. There's a lot of people that just call them voltage controlled resistors, and that describes their behavior a little bit better. Keep in mind if you're trying to use with low level hobby electronics, that's like 3.3 and 5 volts. or just logic signals in general, you'll need one that conducts enough voltage with a gate voltage around 5 volts or even as low as 3.3. Um, Keep in mind that threshold doesn't mean it's fully on, just starting to turn on, but that might be enough for logic level circuits. I just mentioned P-channel, so there's N-channel and P-channel MOSFETs. NMOS refers to N-channel, PMOS refers to P-channel, and CMOS refers to complementary MOSFET, meaning that the circuit uses both. N-channel electron carriers, whereas P-channel have hole carriers. We covered electrons and holes in an earlier video. N-channel, it turns on when the gate voltage is higher than the source. Um, Conventional current flows from drain to source. It has lower resistance, faster switching, low side switching, so you'll probably more likely see N-channel ones. P-channel, it turns on when the gate voltage is lower than the source. Conventional current flows from source to drain. Higher resistance, slower switching, high side switching. So N-channel, better performance, but P-channel has easier control. N-channel pulls the output down, P-channel pulls the output up. Um, with N-channel, when the gate is high, it's on. When the gate is low, it's off. And then P-channel, when the gate is high, it's off. And when the gate is low, is on. You'll also encounter a distinction between enhancement and depletion mode MOSFETs. You're far more likely to be working with enhancement mode MOSFETs, but you really should be aware of depletion modes because you may run into one and wonder why your MOSFET is not functioning like you think it should. Again, always check data sheets. Make sure you know what you're working with. Now, P channel and N channel can actually be either don't assume enhancement or depletion. And people do get these mixed up. They'll think they're simply words for the same thing, and they're not. Enhancement, the default state is off. You apply positive voltage to turn an N channel on. You apply negative voltage to turn P channel on. Now, if you're just working with positive voltage, then N channel turns off at 0, while P channel turns on at the source voltage. Keep in mind, I'm really simplifying that. So if you think of a MOSFET as voltage controlled resistor, then enhancement is normally off voltage controlled resistor, and depletion is normally on voltage controlled resistor. Enhancement mode's good for digital switching, which is what it excels at, power electronics, and a safety default behavior because, again, it's normally off. So depletion actually has some uses. It's really good for constant current. It can handle really active loads at analog circuits, things that are supposed to be normally on. And apparently it even has some JFET-like analog behavior. To be fair, I'm not entirely sure what that means. Here's just a quick picture of N-channel and P-channel. You're pretty much dealing with the same thing with a MOSFET. There's where the gate is. It's made of metal. Then you have the oxide layer there. Um, so yeah, the body and or also known as the bulk. All right, let's go into every circuit here and take a look at our MOSFETs. We've got our N channel here and we've got the P channel here. We've basically got them configured in about the same way. Um, just so I could see the numbers a little bit better, I set the sources to 20 volts. Um, Now the N channel it's hard to set 0 in every circuit. Yeah, I turn 0, it's turning off. There's negligible, let's see, let's wait for the numbers to actually settle out here. But the numbers are pretty negligible. It's not going to light up the light. But let's keep turning it on. Let's turn it to, actually that's millivolts. Let's see when we get to a point where we start to see it glow. I'm starting to see a movement there at 4. 2 milliamps, 1.76 volts. So in real life, this would probably start to be glowing at this point. Let's keep turning it up. Now we can actually see it. All right, milliamps is still kind of low, but our voltage is on point. Let's turn it up again, 7, 12, and almost 2. At this point, we're in saturation range. So let's put it on 8. And that goes pretty good. That's 17 milliamps and about 2 volts. This would be shining bright in real life. All right, so that would be safe. Mind you, this is a 20-volt source too. Okay, now let's look at P channel. We've got our 20-volt source. So let's actually start this off on 20 volts at the gate. So basically it's completely off, or as off as it can be. So let's start turning it down. Oh, that's 10. Let's see. All right, we're starting to get a glow here at 16.3 or so. Actually, see what it looks like at 17. That's still a glow. Let's put 18. That's 1.72 volts, 1.37 milliamps. In real life, we would probably see it by now. Let's turn it down more. Turn it to 16, 5.74 to 15, 14. Now we're already going into kind of saturation range at this point, but this would be pretty bright. Let's go to 13. So kind of sort of at the same place. Well, let's go down to 12 actually to see what our difference is up. This is we've gone up 8, and this we've gone down 8. So yeah, 19.2 milliamps, 2 volts, somewhat close between the two. For again, this would be really bright LEDs in real life, and these aren't based on any specific model. All right, let's look at Falstead. We've got N channel over here. We've got P channel over here. In this case, I'm just going with the 5 volts, so Arduino friendly voltages. So in the case of we have it at 5 volts full on the N channel. It's fully on. It's 1.8 volts. It's 12.5 milliamps. So probably pretty close. Again, this is just to match it. I don't think, let's see, let's turn it down and see. Yep, that's not gonna do any better. But yeah, as we bring it down here, it eventually gets pretty negligible. LEDs work a little bit differently. I would say a little closer to real life since they're still staying lit even when it's very negligible. But yeah, we get it down to zeros in the nano amp range, so basically um, less ampage than I think humans can. We get wrong on that, but we still got a lot of millivolts here. Well, let's look at the other thing, the PNP. So it's fully on at 0 volts. We're getting 11 milliamps, 1.8 volts. This would probably be fairly bright, real life. And oh, okay. And as we turn up the voltage, everything goes down. So it works in the opposite way. Plus, mind you, I think drain and source here, whereas it's the source here and the drain here, I believe. Yeah, source is on top, drain is on bottom for NPN, and drain is on top for excuse me, P channel. Source goes to drain, and N channel drain goes to source. Gate is always obviously always in the middle. Here, let's take a look at QSpice here. In the case of QSpice or any spice simulator, you can actually bring up a model of a specific MOSFET, which you're going to see a lot more realistic numbers. I've got a IRL Z44N, which is common enough to find for logic level here. And since we're looking to do logic level work, I'm setting a source of 5 volts. And we've got a gate with the other, which can go we're setting it from 0 to 5. I'm going to be watching the drain and the current of the light and see where the best result that we actually get. All right, let's look at our numbers here. On the bottom is where we have what the gate voltage is. So we're starting at 0, which we've already got 300 milliamps, which again, if we looked on Falstead, that's actually pretty close. Sorry, millivolts. And then we got 0 milliamps. So basically at 0 volts, it's completely off. And then we start to reach a point, it just starts to turn on, or at least in terms of it increases the volts. So the volts keep going up. Then it reaches a certain point here where it goes sharply on the current, not so sharply on the drain. And at 2.1 volts, we're about as on as we can get. So this area here is the active, and then past that is saturation, and then oversaturation, I guess, too. So yeah, 2.1, 2.2 volts. We're getting close to 20 milliamps and about 720 millivolts, which, yeah, we could still get a light on. And keep in mind, this model, or even the way that I'm using it, the numbers might not be quite right. All right, we're working with another model here. I believe this is P channel, if I'm not mistaken. Yep, source drain. Okay. So this one, well, let's take a look. We're going to the gate. We're going to start at 5 and we're going to move down to 0. So we're going to do it in the opposite way. All right, so here, let's look at the numbers. When we're at 5 volts, we're effectively off, say, like 400 millivolts or whatever, and then no current. Keep going, it's still essentially off. Then we reach a certain point where it starts to turn on. And it does it pretty sharply, actually. So about 2.8 volts on the gate, and we're getting 5 volts on the drain, and we're getting 13 milliamps on the light. So this would be very fully on. All right, so just to wrap things up here, transistors are three-terminal semiconductor components that allow a smaller signal to control a larger one. They can turn stuff off, turn stuff on, or just amplify a signal. First transistor was point contact, came out in 1947, and quickly hobbyists started to be able to make it at home, although it wasn't super practical. Bipolar junction uses 3 layers. It's NPN or PNP. It basically made transistors practical for electronics, um, without which, like the miniaturized radio, wouldn't be possible. Um, Mind you, be really careful with the packaging. A package is just a package and it can house many different types of components entirely. So just always check those data sheets. And if you don't know the data sheet, get your get something out to read off the numbers. Um, you'll find plenty of cheap variety packs of JPTs and MOSFETs for hobby use. There might even be ones for JFETs. I'm not entirely sure. We also mentioned FETs, that's field effect, where basically there is an electronic field between two of the same type, so N type and N type. That's where it allows the flow. They use a source gate drain or drain gate source. Um, and they're controlled by voltage instead of current. We mentioned MOSFETs, and the MOS part is metal oxide semiconductor for the gate. MOSFETs made microscopic electronics possible and far more efficient. We talked about other types, JFETs, FinFETs, IGBTs, HEMTs, GOFETs, etc. Always be careful that the transistor works at logic levels or low power, especially if you're working with just 3.3 volts or 5 volts. And I guess that wraps it up. So have a good one.